Welcome to LEGO Biomechanics. Today's topic, angular motion. This isn't the revolution I was hoping for. If only I knew how to describe angular motion. Actually, we already do know how to describe angular motion. Just like with linear motion, how we use position to calculate displacement, velocity, and acceleration. Now that we know angular position, we can use that to describe angular displacement, angular velocity, and angular acceleration. Here, let's look at this example. I can open this up in a program that will let me look frame by frame, establish my global reference frame and my local reference frame, and since I know the frame rate is 240 frames per second, I can count frames to establish the time. So now all I need to do is track my angular position from frame to frame. Let's keep track of it with this handy little table. Since I'm going to call this my first frame, this can be frame 0, the time can be time 0, and my angular position can be 0 as well. Now I skip ahead 12 frames, I'm at time 0.05 seconds, and I have an angular position of 30 degrees. Sorry, I mean pi over 6 radians. Now I can repeat this process for 12 more frames, and 12 more frames, and 12 more frames. And when it's all said and done, I can put together a graph of my angular position versus time. I can tell a lot about the angular motion of this brick from this graph, just like I could tell a lot about the linear motion of a brick using the position versus time graph. The vertical difference between any 2 points represents the angular displacement, or the change in the orientation of an object over time. The horizontal distance between any 2 points represents the change in time. Since angular displacement divided by the change in time equals the angular velocity, I could calculate the angular velocity from this graph. If I fit a line to it, the slope of that line equals my angular velocity. And finally, if we have a straight line, we know that there must be no angular acceleration because the angular velocity must be constant. For another example, take a look at this brick. You'll notice that it is rotating in the opposite direction and it is rotating more slowly. When we repeat the steps we just took, you'll see that not only is the slope less steep because the angular speed is slower, but it's also sloping in the opposite direction. It has a negative slope because this has a negative angular velocity. So to recap some key points, our angular displacement is our change in angular position between 2 points in time, similar to the way displacement is a change in a linear position at 2 points in time. Angular velocity is equal to an angular displacement divided by the amount of time that angular displacement took, and that counterclockwise rotations lead to positive angular displacements and angular velocities, while clockwise rotations lead to negative angular displacements and negative angular velocities. Thanks for watching. See you next time.